Good evening, ladies and gentlemen, and welcome to the SAIEE Central Gauteng Centre's webinar on impact of inverter-based generation on grid stability. Before we start, a few webinar considerations. Attendees are reminded to ensure your volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the the Central Gauteng Centre playlist. This channel is updated regularly, so ensure you check back as often as possible for new uploads. A link has been provided in the chat box to subscribe to this channel, and it's free. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now to the host for tonight, Mr. Khomotso Setlapelo. He is the Vice Chairman for the SAIEE Central Gauteng Centre. He is a registered professional engineer with the Engineering Council of South Africa. He is a senior member of the South African Institute of Electrical Engineers and, as I've mentioned, Deputy Chairman of the Gauteng Centre. He is a former Chairman of the SAIEE Events and Media Committee and was the Program Chairman of the inaugural SAIEE National Conference in 2019. In 2017, he was awarded the SAIEE Keith Plowden Young Achiever of the Year Award. He was also listed on the Mail and Guardian Top 200 Young South Africans for 2018. Over to you, Khomotso.
Thank you very much, Minx. Good evening, colleagues. Welcome to the SAIEE Gauteng Centre. Thank you for joining in your numbers. The numbers are looking quite good. We appreciate you coming, and we hope to also see you in person when we host our events. Mostly will be at the SAIEE Gauteng Centre, or at the SAIEE House in Johannesburg. We do not want to waste too much time. I think, yes, Minx will speak about how you can subscribe to the various channels that we have as SAIEE and how you can also join. And if you're not a member of the SAIEE, become a member of the SAIEE via the SAIEE website. So without wasting too much time, I would like to introduce our main speaker on this very topical subject on inverter-based generation and its impact on the grid. Our speaker is Mr. Mpedi Rampokanyo. Mr. Mpedi Rampokanyo is a professional electrical engineer from South Africa. He's an electrical engineer with 17+ years of experience in the power sector, focusing on renewable energy integration and power systems operations. He has a BSc in electrical engineering from the University of Cape Town and a Master of Engineering degree in electrical engineering from Wits University. He's currently working as a managing director of Rampox Energy Pty Limited, an engineering, construction and consultancy firm based in South Africa. He previously worked at the CSIR, the Council for Science and Industrial Research, as a principal engineer at the Energy Centre in South Africa, providing research leadership in the area of power system operations in terms of model development, standards or codes, regulations, and policy issues for the current grid and future energy system with a high share of renewables in support of the country's energy goals. Mr. Rampokanyo started his career as a power systems operations specialist at Eskom. He worked for 10 years in ancillary service reserve requirements, renewable energy and system inertia studies, generator special protection schemes, transmission network constraints, and IPP integration studies. He was a convener of a SEGRA joint work group C2/C4.41 and an international working group focusing on the impact of high penetration of inverter-based generation on system inertia of networks. That concluded and published work in October 2021. So I think we have we're very proud to have a specialist in this subject who is very close to us and who is working in South Africa and as part of the SAIEE. So without wasting any further time, Mr. Rampokanyo, please take over.
Good morning, colleagues, ladies and gentlemen. Thanks a lot, Komuto, for that colorful introduction. Yes, the name is Mpedi Rampokanyo, and I'm going to take you through the impact of inverter-based generation on grid stability in South Africa. I'm going to share my presentation. So I hope everybody can see my screen. Yeah, so the topic of, yes.
Sorry, just change your display settings because we see your presenter view, not presentation view. In the top in the middle, go to display settings.
Okay, still on. Okay.
If you go to your left, above the presenter view, go with your mouse to the left. You've muted yourself. I can't hear you.
Oh, sorry. Can you see my presentation?
We see the presenter view, not the presentation view.
Oh,
You have to
okay.
display settings. You've got to swap them.
I have to swap them. Okay.
Second thing, top left.
Yes, go more to the, yeah, move that away. Yes, click there.
Oh, okay.
Top way. Swap, no. Okay, perfect. Just move your GoToMeeting using the webcam notification off there. You've got a green GoToMeeting. No, the green GoToMeeting banner you just moved is over your presentation.
Oh, okay.
Yeah, just move that off the screen. Thank you, sir.
Okay.
Now you can continue. Thank you.
Okay. Okay, no, thanks a lot. Always challenging, with this technology. But yeah, okay, we can shoot, I think. Okay, yeah, so it's the topic of today is impact of inverter-based generation on grid stability, focusing mainly on South African grid challenges. Yeah, just to take you through the presentation outline for today, I'm going to take you through the background on energy transition. I'll touch on power system stability, since it's the topic of today, mainly focusing on frequency stability and erosion of inertia. So I'll go through some background theory on this. I'll touch on inertia and practical implications thereof, and a few international experience in terms of this erosion of inertia on the power system. I'll also touch on mitigation options, because it's no use talking about the problems with no, solutions. So we'll look at different mitigations to basically, mitigate this problem of inertia. We will touch on frequency response and practical implications, new ancillary services suits, grid code considerations, and lastly, some key takeaways and conclusions. So as we know, the energy of the world is transitioning. Transitioning into a new mix of resources in the world. Everybody is seeing this happening. So there's this big global drive to reduce carbon footprint in the environment. We know that the world is looking at alternative sources of energy that are less pollutant and cheaper to harness. We are seeing widespread introduction of renewable energy sources as alternative energy sources for the future. The electricity sector is one of the big off-takers of this primary energy source. And the introduction of this new generation, which largely is inverter-based, onto the grid brings with it some challenges and some benefits. So today we'll be mainly focusing on the challenges that these new energy resources are bringing onto the grids. But we know that obviously there are a lot of challenges in as far as, or rather benefits in as far as renewable energy is concerned. So if we look at the IRP here in South Africa, the 2019 IRP outlook, I just took a summarized outlook showing how the energy resources or the energy mix are panning out until 2030. So if you remember well, we had previously the IRP 2018, which was a draft IRP that went up to 2050, if I'm not mistaken. But then I think the promulgated IRP is now going up to 2030 simply because there were problems of stability going beyond 2030. So that's why our current IRP only has an outlook up to 2030. So if you see the picture there on the screen, you can see a steady increase of renewable energy or uptake of renewable energy as we move from 2018 until 2030, with declining coal-fired plants. As you see, I think the bottom of the bar is representing coal. So it's a steady decline. It's not anything to write home about at this stage, but yeah, there is definitely a decline of coal plants as we retire them and make way for renewable energy resources. So we are seeing that the problem that we are dealing with here, which is inverter-based generation, impacts up to 2030 might not be so bad given this picture that we are seeing, but certainly it warrants a concern for us to start now doing some thorough planning and proper studies in this regard. So we got two drivers that are driving the energy transition. So basically, it's finite resources and emissions control of CO2. Those are our primary drivers, being a price control, price pressure, and regulatory policy. So that is what is actually driving this whole energy transition, finite resources, and we also want at the same time to make sure that we reduce our carbon footprint on the environment. So that gives rise, obviously, to price pressures and policy or regulatory issues. And then from that, there are two resulting mega trends, which is energy efficiency and renewables. On the one hand, we also want to make sure that we are energy efficient with the energy that we have. And at the same time, we are moving away from conventional energy resources into this new renewable energy resources that are more, have a better footprint on the environment, such as you know, PVs, wind, biomass, hydros, and so on and so forth. And then, obviously, in terms of the vision of where everybody else is going, we want to now make sure that our current industries are now supplied from renewable energy resources, as you can see on the picture there, that now we are moving to a world where we won't have fossil fuel resources driving our primary industries, as you know them, such as the transport sector, and so on and so forth. We are basically moving to a world of renewable energy where we will be green. We'll be green, as the word is saying. We want to be green. So it's a very, very a good initiative for the world, I guess. In terms of our current architecture of the electrical grids, we currently have a big transmission backbone that is normally centrally controlled. And you find that our customers are feeding off from this backbone. And we have central control. We have one national control that controls the whole grid. So that's currently how a conventional system looks, but we are moving away from this. As you know, we are moving into a future where the architecture now is no longer centrally controlled, but is more decentralized, and we are looking at things like microgrids that can easily island and to an extent autonomous and can generate generate power on their own and consume on their own. But at the same time, we are looking at a future where this particular microgrids will be transacting or intertrading amongst themselves, in as far as energy is concerned. So, for instance, if there is a big event in the network, then the nice thing about the setup is that you find that your microgrid, because it's a decentralized control, can easily island and then supply that particular, the customers in that particular microgrid. So this is the world where we are moving. Currently, we have seen a lot of uptake in the sub-Saharan region of this microgrid, especially for remote rural areas. There's a lot of projects going around ahead in sub-Saharan Africa and Africa as a whole. In South Africa, a few of them. I've been privileged to be part of a few projects here in South Africa concerning microgrids. Yeah, and then in terms of the South African energy balances, in terms of what is it that we are reliant on, you will see that I did this analysis, I think, around 2019, although I used data from International Energy Agency, IEA, that was 2015 based, but I think the picture has not changed that much. I did this in 2019, close to 2020 or so. And then this was the picture that we're getting in as far as South Africa is concerned. You can see there's a big reliance on coal. It's the driver of basically the industrial sector, transport sector, commerce sector, residential, agriculture. You can see all of those sectors are relying on the production of electricity from mainly coal. There is a slight uptake of renewable energy if you look at the picture there, but it's not anything to write home about at this stage. So even now, I think we are sitting at around 66 gigawatts or so, to 7 gigawatts or so, if I'm not mistaken. The ESCOM people know the right numbers, but I think it's around 6 gigawatts of renewable energy at this stage. So we are still not yet progressed. Obviously, our IRP has big ambitions in terms of uptake of this renewable energy. But this is where we are sitting currently. We are relying on this. And I did this, it's just that I was not, because of time constraints, I couldn't share you the energy balances for other countries, especially in the BRICS, a group of countries. I did that analysis there. I can tell you there is still a lot of reliance on coal with the BRICS, with Russia being an exception in that they tend to rely more on oil. So you find that their primary plant is mainly driven by oil, and they have a lot of district heating that is a takeoff of that energy. So yeah, so that is in line, I think, with Europe, where you have a lot of this district heating. But there's a lot of reliance on fossil fuels. I think that's the point I'm trying to make. So now touching on the problem or the discussion at hand, power system stability. So power system stability is defined as the ability of an electric power system for a given initial operating condition to regain a state of operating equilibrium after being subjected to a physical disturbance, with most of the system variables bounded, so that practically this entire system remains intact. So this definition is given by IEEE and SAIEE. So as you see there on the picture, we have power system stability having three components, which is the angle stability, the frequency stability, and voltage stability. And so our concern here will be mainly on frequency stability. Not to say that the other stability do not come to the fore. So basically, as electrical engineers, as we know, as engineers, if you remember, we normally use the theory of superposition. So basically, we tend to look at things from that we single out an entity so that we don't confuse ourselves with analyzing problems, especially complicated problems like this, holistically. So we try to simplify the problem by using superposition theorem. So frequency stability, even though we are looking at it, it doesn't mean that it doesn't affect the angle stability. Obviously, frequency relates to angle, it relates to voltage. So if you have a frequency stability problem, all those other things are going to be affected. But to solve the problem, we need to find out the root cause of the problem that we deal with, and then that's when we'll apportion and say this is an angle stability problem, or it's a frequency stability problem, or it's a voltage stability problem. But the effects would be that all stability is affected the moment you have an instability in a network. So in frequency stability will be there is the short term and the long term. Our focus is going to be on the short term, which is more on what is called a primary frequency response, while long-term stability focuses mainly on system flexibility, which is regulation up and down of trying to balance the system, when you're regulating up and down with generators that can ramp up to correct the frequency. That is more in the secondary frequency control region. So we are not going to be focusing on that. We are now going to be focusing on the primary frequency response. The famous equation that almost every engineer would know from electrical engineering that governs the dynamics of the machines with the interaction of the network. We know that it says that the accelerating torque of a machine is a resultant of the input mechanical torque together with the opposing electrical torque that is developed across the terminals of the machine. So there it says TA equals to your mechanical torque minus your electrical torque, where the electrical torque is resultant and it's normally opposing to the force to the mechanical input torque. I think it's I might be mistaken. I'm not sure if it's Faraday, but it also comes from the third law of physics. But anyway, so that can easily now be derived into accelerating power being mechanical input power and minusing electrical output power. So that because that is so because of the relationship between power and torque, which basically would have a speed as the constant. Yeah. So that's how it is. So this is an equation that governs machine dynamics. So in terms of frequency stability, we know that there's always a concern to balance supply with demand. Obviously, that's why we're having this series of load shedding, simply to balance supply and demand, where we have currently constrained supply. So because of that, obviously, we have to load shed. Eskom has to load shed. Let me not say we. Let me say Eskom has to load shed to balance supply and demand. It's our problem, though. We all have to own it because we are sitting with these constraints. It's simply to balance the system, because if they leave it if demand exceeds the supply, they will collapse the whole system, and that would be very irresponsible of them, and could lead to basically the whole country blacking out, and then we having challenges in terms of bringing the system back. You know, a system as big as South Africa could take, I'm sure, some days to weeks before it gets back. So we don't want to see that kind of thing. So we have to bear with them in terms of what they're doing. Although, yeah, we are getting impatient and we need a generation to come on board so that now this problem can be a thing of the past. Yeah, but that's what's happening. As you can see there, the scale that I've shown there, just to illustrate the concept. If you have more generation, you'll see that the frequency will tend to become more, you know. So your nominal frequency is 50 hertz when the system is balanced, and then if you have generation more, then the frequency increases. As you can see, that the scale will tilt towards the right, and then if you have a more load, then the frequency will decline, you know. So we want the system to be more or less around 50 hertz nominal at all times. We don't want the load to be excessive. We don't want the generation to be excessive, because all those things are bad. But currently we are seeing a lot of, we are managing the low frequency problem with the load shedding, where the load or demand is greater than our generation. So that's just an analogy there that makes it easy for people to follow. And then in terms of the supply side, we know historically that it played a very dominant role in frequency control via governor action. So basically, generators are all equipped with a governors, what we call governors. It's a circuit that controls the valve that leads as steam into the turbine from the boiler. So there's a valve there that is of interest for electrical engineers that we always want to model, and that valve, we control it using control systems. The position thereof, you know, in terms of how much steam you allow. So we want that process to be automatic. So that's where now governor control comes in. So traditionally, that's how we've been sort of like managing generator dynamics using a governor control. And then also on the demand side, what happens is that we have different load characteristics. You have loads that are responsive to frequency, to voltage. You have some loads that are non-responsive to that. So the red graph there or line will show your load that is more or less resistive, that is non-responsive to frequency, and so that means even if your frequency changes, it doesn't change. But generally, you'll find that load normally, like motor load, would change with frequency. It gives you a bit of relief, we call that, because if the frequency declines, then that load as well declines, reduces. So by doing so, that means your supply-demand balance now gets relief. You know, you don't no longer get a strain on the system if you have frequency sensitive load, you know. But the actual load is a mixture of that, because you have some loads as non-responsive to frequency, and other loads being frequency responsive. So then you have a combination of that, which is that green line there. So you do get sometimes a load relief. So that all that it means is that if you have a frequency deviation, you're going to get relief on the load, because it will reduce. So if it reduces, then it gives you relief in terms of the balance in the system, which is a good thing. It's a very, very good thing if you have that kind of load. So then when we do our models, obviously we have to model that what you call load frequency characteristics in terms of the responsiveness of the load to frequency. And then that will give us a bit of relief. So that's what the load does. That's what the load does. But this classification, I must say, is not an easy one, as the load is not always, the data on the load is not always easy to get, you know, to find out how the distribution or the type of loads that we have in on the network are. It's always a mammoth, but yeah, there's some guidelines in terms of determining that frequency sensitivity. An important characteristics of the power system is what is called system inertia. And what is this system inertia? Inertia is defined as a body's resistance to change in motion. So basically, if from physics, you know that when you're talking inertia, if you have a body at rest, you always need more force to move it up until it gets moving, you know, and you've overcome the coefficient of static friction, and then now you experience what is called coefficient of dynamic friction. You find that your curve in terms of force, it will increase high and then decrease once you're in motion. So that is inertia. So it's always difficult to start things off the ground and then to stop them. You know, that's what inertia does. You know, it's a mechanical concept. So basically, any body has inertia. The more mass you have, the more inertia you have. So you can just see, even with our generators, because they've got rotors that are rotating and their mass, they've got greater mass, especially because now remember the main thing about the rotation is that the rotor is actually coupled to the turbine. It rotates with the turbine, or it gets the rotation from the turbine as the steam hits the turbine. And the turbine is more massive than the rotor. It's more massive. The rotor would be on the order of 1/3 of the turbine mass. So that's where the inertia comes from of the system. The inertia of the system comes from mainly the turbine. The rotor gives a bit of it, but we are looking at the turbine. So the bigger the system, the bigger the plant is. 600 megawatt plants that we're having in ESCOM would give a lot of inertia onto the system. So that's what we are looking at here. So the more or the challenge is that if you start reducing this or displacing this, a conventional generation with inverter-based generation. Inverter-based generation doesn't have rotating parts, so that means inertia is absolutely zero. So that becomes a challenge, as we'll see. So yeah, so in terms of definition, we have what is called the H constant on the generator, which is the stored rotational energy over the MVA base of the machine. So that is at the machine level. But at a system level, we have the summation of what we call rotational energy of all plants, which is H times MVA of each machine. And then we divide by the system MVA. That will give us an equivalent H constant for the whole system. But this formula ignores what is called load damping effects. It doesn't include inertia that comes off from the load. As I've said, that motors obviously are rotating, they will have inertia. And we have big industrial motors. So unfortunately, because we don't have enough data to can make or measure inertia contribution from the load, we tend to use this crude estimation. It works, we understand the error. So if the error is constant all through, and then we are analyzing that constant error, obviously, we will get somewhere for as long as the error is constant. So that is well acknowledged. But there are efforts, obviously, to measure inertia and to basically online on the system to get more accurate estimation of inertia. But currently, everybody uses, or most of the people use unit commitment, which is basically inertia coming off from our generators alone, with an understanding that it's a crude assumption, but that's what we are working with currently. So some salient points to remember about why inertia is important. So inertial energy in the power system helps in arresting frequency deviations. And a heavily loaded system is stiffer to frequency excursions than a light loaded system because of the larger amount of rotating machinery in the former. The load frequency characteristics and inertial energy in the system help in damping smaller frequency excursion even before primary governing can activate. You will see this as time goes, how it comes about. The displacement of synchronous generation with static, that is non-rotating generation, which is inverter-based, resources like wind, PV, batteries. This substitution of inverter-based generation leads to high erosion of natural system inertial energy on the system, and hence the system becomes more malleable to frequency excursions, more especially under light load conditions. So our worst case conditions is when we are light. So light meaning that the system has less load, has minimal load. And by virtue of that, that means you won't have a lot of synchronous machines online, and you won't have a lot of rotating machinery online. Like for instance, around December holidays in South Africa, you find that a lot of plants will close, a lot of generators now will pull back because there's less demand. That's when now we have problems. And then that's when maybe you have a lot of, now with the renewable energy, maybe deployment of a lot of renewable energies, inverter-based resources. And then we'll sit with a big problem. Even with low penetrations, we might start having big problems, because at an instant, you may find that even though maybe we have something like 10% penetration levels, at an instant, it can easily become 30%, 20, 30%, very easy, at an instant, if you're looking at the time distribution of the load, as time goes. So that becomes a bit problematic, even at these low levels. So the SAIEE Grid Code states that the requirement on the system operators to keep the frequency above 49.5 Hz following all credible single contingency losses. The largest loss being the loss of cubic unit at full load, which is like 920 megawatts. So that's the credible contingency, obviously, that I think ESCOM would use to define the primary reserve. So for low frequency event, primary frequency reserve can thus be defined as the amount of primary governing response required to turn the frequency at 49.5 Hz following that credible contingency. So that picture defines that. The top one, obviously, that amount of reserve that you carry. So this is not particularly the South African system, but it was just for demonstration purposes. It's some study that I did in the Sub-Saharan Africa. Obviously, for propriety, I won't really share what it was, which country it was, but it was a small country. Yeah, so basically, the turbine power will move from where it was, and then automatically the governors will start injecting more power due to that disturbance. So basically, you want to define the reserves as the Grid Code gives it to turn the frequency at 49.5. You're saying what you find for that particular credible contingency. If it does happen on the system, it should be such that we have enough capacity in terms of reserve on the system to can be able to turn the frequency at 49.5. So then you will have, the way they do it, you will just have your governor, your machines that are contracted for that reserve, they have to pull back their power output. So basically, they are not allowed to generate at full output. They will have to carry the reserve. So when they carry that primary reserve, they will give us something like 5% margin or so below their maximum continuous rating. And then that will be the amount of reserve that they will respond by in case something happens. So it's automatic. So in terms of the ancillary services suite, which is conventional, which is what we have now, we have what is called the primary frequency reserve, which is a governor action, as you can see on this graph here. And then we have what is called secondary frequency reserve, which is now the action of what is called the AGC. And then lastly, we'll have something that is more tertiary reserves, where units can be called upon to supplement and bring the frequency back online. So primary frequency reserve happens automatically. And then the initial thing that you have to notice is that before the reserve can kick in, actually the system is helped by the inertia of the machines themselves, by that tendency to refuse change in motion. So basically the machines are rotating, and then there's an imbalance when you lose maybe a particular large generator, for instance, you will have a system imbalance, because now there's the supply demand balance will be disturbed. So once you have that, then the frequency will start declining. But the decline and the machines will slow. And when they slow, because now they have this inertia or rotational energy on, they'll be releasing that rotational energy. So that happens at an instant before governor action kicks in. So the mechanical resistance of the rotation of the turbine with the rotor will assist the frequency decline. We have been seeing this all the time. It was a freebie we didn't even care much about, but now it's so important that we have to worry about it now, because we are seeing systems becoming very, very, very responsive to frequency excursions. And we have a danger of having, if there's too much decline, it will result in a generator tripping off and rock off, because there's a limitation in terms of how much frequency can run off in terms of, DFDT, basically the rate of change of frequency. If it's too excessive, then there are some generators take themselves off, and then will collapse the whole system. So that's the danger with this thing. So this is just showing degrading inertia as we increase penetration levels of renewables. You can see that we have lower nadirs. You can see we're starting off first with a stiff system where the DFDT is quite stiff. That is the rock of the rate of change of frequency. You can see in terms of the stiffness of the fall of frequency that is stiffer, and it gets more steeper and steeper as we increase the levels of inverter-based generation. So inverter-based generation leads to higher rock-off levels. The rate of change of frequency increases this way, and then the nadirs become lower and lower, so which now starts encroaching and violating that Cricote limit that we have seen. Even with the primary reserve that we be carrying, they may not be enough to sustain us to 10 at 49.5, as you can see in this particular picture. That is what's happening. That we are even encroaching on the first stage of UFLS here in South Africa, which is set at 49.2, which is like a safety net in as far as under frequency is concerned. It will take things automatically. So that load shedding is called an under frequency load shedding. It will take off the system, the load automatically to try to save the system if you find that our primary reserve was not able to arrest the frequency at 49.5 and it gets to 49.2, then it will start taking off. But the danger with this is that sometimes the generators may not, it may be too fast for the relays to actually pick up that rock off. If it's too high, then the relays may fail to activate, and you find that now we could sit with a blackout, as you see that it has happened in some parts of the world. For instance, in Australia, in September 2016, they experienced a partial blackout of the southern region, that is the South Australia, when they had about 60% penetration of renewables in the South Australia. So they had a big interconnector with the main Australian grid. So the southern region is about, I think it was about 3,000 megawatts, 3 gigawatts or so. And it connects to the main Australian grid via a couple of lines. I've just forgotten, but it's a Haywood feeder interconnector. So the claim is that they have lost this interconnector before, and they were able to island in the southern region. But in this particular instance, they had about 60% penetration in the southern region. That's where they have a lot of generation of renewable generation. And to their surprise, they couldn't, when they lost the interconnector due to tornadoes, as you see on the picture, they actually lost the whole southern region. And there are studies, that is the AMO, pointed to high rock-off levels, rock-offs of around approximately 6 hertz per second they saw, that resulted in their generators tripping, all generators that were in that particular southern Australia tripped due to this high rock-off levels, and they actually blacked out that portion of the country, and yes, they are they deduced that it was because of this high Rokov levels that were caused due to high penetrations of renewable in that particular region. So I know that there is a lot of contention, even in Australia. Obviously, people that I hope that we are talking to engineers, because we have politicians, we have lobbyists of renewables. Sometimes they may say, no, it's not, it wasn't the case. But well, we as engineers, we have to see things for what they are. But in no way are we saying that we don't want renewables. We actually do want renewables, but we need to plan better. And I hope that the government can give us the space and can fast track or even have programs to start studying this phenomena a bit better in a more organized fashion, so that when we integrate these renewables, we are not caught napping, because that can easily happen. Or integrate at a later stage where we sit with a lot of problems that could cause blackouts. Another interesting incident happened in National Grid, in the UK around 2019, where there were a lot of speculations around what could have caused that, when they lost some of their wind farms due to lightning. I think they lost about 737 megawatts of Hosea wind farm, that cascaded into another series of events, and they saw frequency as low as 48.8 or so. This particular one, I'm not going to go through it step by step, but my quick take when I was reading the report, I thought like it was just not necessarily, although there is an indication that some of the embedded generation, that is the inverter-based generation, mainly wind, tripped on Rokov, but it was not so much. It was about 400 megawatts odd of embedded generation that tripped on Rokov and exacerbated the problem, But it was not necessarily like erosion of inertia like the Australian one. I think it was more on system frequency control that's not very tight. I think they were a bit caught napping then in terms of their tight control measures on management of frequency. But I think since then they went out to market, which is a positive thing. They had a program called the Stability Pathfinder, where they actually were sorting out, were seeking solutions from the market in terms of addressing these stability problems, in as far as Inertia is concerned, to find out if people could start coming up with innovative ways and clever ways to try to alleviate this problem of inertia and stability in general. So they since went out of that Pathfinder program. Yeah. And then in terms of the challenges associated with increasing non-RES penetration, I think we have seen now up to so far is that the biggest one would be the contingency size. The larger the contingency, the bigger the concern. So the larger the contingency in terms of in terms of the generation or the load for that matter, on the high frequency side would be the load, and on the low frequency side is the generator. But if you have bulk generation, obviously you have to cater for it. When you're planning your reserves, you have to cater for the loss of that large unit. So the large generation you have becomes a problem. So if I think we could easily solve this now when we move into renewable energy, and we are transitioning into that world where now you find that generation becomes modular, it's smaller. So it will sort of like take away this contingency problem. We may have to plan for smaller contingencies, which is a good thing. Then obviously this penetration of inverter-based generation, as we have seen, leads to reduction in inertia, where you have lower nadirs and increase in Rokovs. And then frequency control as well becomes a problem. Now more on the secondary frequency side of things, where you find that the intermittency that we are having with renewable energy, when you're having cloud cover, changing weather patterns, you have a lot of intermittency. Then you start having a lot of problems with the regulation of frequency. Yeah, it's a big concern. I know that in one area that I was working on recently, in one sub-Saharan Africa, they were experiencing this, and they didn't understand what was happening, because they were excited when they had renewables coming on board, but now they had to manage the frequency fluctuations because of this changing weather patterns and cloud cover. You find that it comes all over the show. So normally, what you do for that, to manage intermittency or variability, you basically have to have fast ramping machines, and you put them on HGC, so that they can regulate a bit better. So that is on the secondary frequency side of things. But that's very, very important. And it actually, when the frequency goes up like that, then the voltage gets affected, and it just becomes bad. It becomes very, very bad. I think to an extent, maybe ESCOM could be seeing this during light loading conditions at night. I'm sure at control, national control, they're probably struggling a lot with these fluctuations. But obviously, I always speak under correction. The experts there will know better. Yeah, so that is the challenges there. And then in terms of mitigation, of this problem, as I've said, that it's no use simply to talk about the problems with no solutions. The inertia problem, by its nature, it has been a problem. It has not been a problem. It's been there. We've been getting it for free from rotating machinery, but now it's emerging as a new phenomenon that we have to study because of this inverter-based generation that we are introducing. So there are a number of things that the world is looking at, that we in the energy fraternity, especially electrical engineers that are more in power system modeling, and are trying to devise in order to alleviate this problem. So in terms of the survey that we carried on in the secret working group that I was convening, that basically finished its work around 2021, I think. Last year, yes, yeah. I think that's when we finished our work. We did some survey in terms of seeing whether which utilities are more aware of these inertia problems and what are they doing about it. As you can see there, you can see that there is quite movement in this area in terms of monitoring and control. We have the ERCOT, you have the StatNet, AirGrid, Manitoba, ISO, Hydro-Quebec. These guys are all in Australia, Canada, AMO in Australia. They're all monitoring. The challenge with this thing is that it's mainly prone to areas that are weakly interconnected with their neighbors. So if you have a system, especially Central Europe, where you find that you have a meshed system, like maybe, for instance, I like to make an example of Germany, which is I think Tenet would be in Germany, yeah, but in Netherlands, yeah, I think Tenet operates between the two. And Amprion is in Germany, and Tenet is it's in Netherlands and Germany as well. But there you find that the guys that I've been exposed to and I work with, you find they don't worry a lot about these inertia problems because they're meshed, and if they have an event on their system, they have strong interconnections with their neighbors, so they're able to get that power very quickly from their strong interconnections. But if you're weakly connected, that's where the danger is. you don't have support from your neighbors. So when you have an event and you're not caring enough, or you have high penetrations of renewables and the rate of change of frequency is high, the frequency falls sharply, then there's no assistance. There's no immediate injection from your neighbors because you're weakly connected. So you find that areas that are weakly connected, grids that are weakly connected with their neighbors are the ones that are prone to this. That's why you have the leaders such as Agrit, in Ireland, being obviously an island, being at the forefront of this. That's why you have AMO. They almost lost, or they lost a portion of their network due to this as well. They're in the forefront in terms of devising mechanisms to do this, to alleviate this problem. Canada, Hydro-Quebec, I think the Canada as well might not have a strong interconnection maybe with the US. ECOT, on the other hand, yes, as well, doesn't have a lot of strong interconnections. Kaizo, they don't have in the main US system. So they're almost like Ireland. It's like South Africa as well. We are weakly interconnected with our neighbors. In fact, we can't get any support from our neighbors. So we better plan very well so that when we integrate these things, we are able to can solve this problem. Otherwise, it will be a problem of that situation where we will be caught napping, where we have a lot of these renewables. And our responsibility as engineers is obviously try to communicate these things to the relevant parties, to DOE, to government, to management. I know that I've been in ESCOM. I know they are probably more compromised than everybody else. They know about these problems. I know I worked with them and I started doing this work while I was in ESCOM system operator. But the challenge with them is that because of the outlook now, or the public image, and obviously because of the interests around these renewables, they are very compromised in saying that we have an inertia problem. Then people think like they're hiding behind it, while it's actually something that we need to worry about. So those kind of politics, I think if engineers come together, especially in this field, and start talking more about them, so that now our politicians and government understand that we have to, even when we are putting these renewables, we do it responsibly. And they fit in, or they put in funds for people to do studies and proper studies, so that these things are integrated in an organized fashion, like the Agrit is doing. They have a program, the DS3 program, where government is largely involved. They fund their universities, they fund the Agrit guys, which is the system operator there in Ireland, to do this thing. And there's a perfect understanding that if inertia levels like they monitor are violated, they will start curtailing wind. They easily do that. They always have when they're integrating, they always have an inertia floor, a minimum inertia level in the system. They used to, when we visited them in 2017, they had it at around 60%, penetration levels. And there was an understanding that if at an instant they exceed that, they're curtailing. And there's nothing about dimmed energy. There's that understanding from everybody else. So all stakeholders are involved, including the IPPs. They're looking at ways to stretch that. I think they since stretched that to around 70% as a minimum inertia. So that they're pushing the boundary, and they're doing it in a uniform pattern. So I know the challenges in Africa, but we need to start talking so that the government can understand that we want renewables. We are struggling now with a constrained capacity, but we need to do this thing responsibly and in a uniform pattern. So that's what the international experience is. We're seeing again a procurement of these reserves from those type of countries, the AMOs, your Statnet in Denmark, ECOT. They have a market-based system where basically they go out to the market and they start getting the services in terms of innovative, techniques. And then obviously there are other methods like the reliability, where you put stuff in the grid code and you will basically define the reliability margins, and you will start probably managing inertia from that point of view in terms of curtailing and all sorts of things. Or sometimes you mandatory force all generators basically, or to start participating, you know, in this type of things. Technologies, obviously, it's a synchronous generators. They would give these services in terms of response, you know, primary response. The load as well, demand response helps a lot, big time, if it's done properly and it's tuned nicely. In fact, it can become fast frequency response, you know, demand response. South Africa does have a demand response already in place, but obviously it's not fast. They will, to manage this inertia problem, they will need to make it a bit more faster and model the relay so that now they trip the load a bit at a faster rate, you know, so that it can be regarded as a fast frequency response. But there is that opportunity, and there is currently Eskom only sort of, it's almost like a closed market. So as time goes, I think the ancillary services market will start opening, where now you have a lot of participation coming from the industry in terms of solving these problems. Yeah, so the best as well, batteries, you'll see there's some studies that I did for battery that can alleviate this sort of problem quite easily as well. And yeah, fast frequency response, I've been talking about this. What is it? It's just power injected or absorbed to or from the grid in response to changes in measured or observed from frequency or observed frequency during the arresting phase of the frequency scaling to improve the frequency nadir or initial rate of change of frequency. So basically just a fast action. And that fast action, unfortunately, we can't get it in our governance, because I mean, like, they've got time constant. The governor valve is a time constant, you know, and obviously it's a design time constant, and we can't get away from that. I know that there are fast valving techniques that you can deploy sometimes, but they are they could be very expensive, because we might have to modify the whole plant. But currently, yeah, we are limited because of that. So we have to look for alternatives like fast response systems, whereas there's things like the load, the BESS, you know, battery energy systems, they're more faster. And yeah, the characteristic of this is that sometimes it can be static, sometimes it can be dynamic, you know, meaning that it can be like one solid load, or sometimes you can have a load and then you maybe put a troop of sorts, and you trip a portion of the load, or it dynamically checks the frequency and trips portions, or stepped, you know, in a stepped fashion, you know, in one particular load. If you have those, you could do those kind of arrangements, you know, so that would be considered a dynamic response. So there's a lot of clever things that you can do in as far as this is concerned. So here it's a study that I did on a test network, just to show how demand response can alleviate this problem. The base was the blue line there that didn't have any demand response. So the moment you start putting in demand response, but with that is slower, with the small delay times, then you find that it doesn't necessarily arrest your nadir, but it improves the frequency recovery a lot. But as soon as now you increase your delay on the relay, that activates your demand response, then you find that you get an improvement on the nadir and the frequency recovery as well. So that is the red curve there. So you can see that now an improvement of something like 120 millihertz for this test case here was achieved with a fast demand response relay. I think my delay time was around 1 second, and then the delay time where you didn't have an improvement here on the red one, so on the what is this, the green one, the delay time was 4 seconds there. So the 4 second delay seems to be the default for this type of things, but it's not fast enough to can act as a fast frequency response. So we have to go to something like a 1 second and even below, like maybe 500 milliseconds, a few cycles, you know. Yeah, so that's the reason you have to be for fast response. And then in terms of energy, battery storage systems, to assist as well, I did some study in some sub-Saharan country, and there you'll see that there is a large improvement. You'll see that the bottom case is where your reserves are very constrained in terms of governing. You have little, and then your frequency nadir is very, very low, below 48 hertz. And then the moment you start to put a bit of governing, in fact, it was maxed out here because they were quite constrained. So then that maximum governing improved a bit, but then see the green part is where now the battery came in. You know, the battery deployment, it was around 25 megawatts. It was a small system, but look at the change. And I can tell you now the maximum governing here was way above 25 megawatts. It was around 30 megawatts. But look, I mean, the response. And with the 25 megawatts, because it's very fast, you know, the battery, when you deploy it, it simply takes the frequency very, very high. Look at the improvement in the nadir. It's very high, very high. So that shows the power of the batteries in trying to alleviate this problem. There are converter control philosophies that are coming on board. Like, for instance, you know that primarily our inverters were grid following. Majority of the at grid scale, more so especially, majority of the inverters are grid following, and as a result, they cannot island. They can still provide some services, but the fact that they cannot island is a big problem for us. So now the new development is that now grid forming inverters at grid scale are being developed, and this will have a lot of advantages because now they're able to sustain the voltage and the frequency themselves. They don't rely on the grid, and then they will be able to deploy this or these services more easier. So there is that a move to grid forming a control on the inverters, you know, that are coming, the new ones that are coming. At residential level, I know that a lot of them now are coming on, where houses can easily, during load shedding, can still supply. But if you have a grid tie inverter, even during during load shedding, then you're off, you know. So that's what's happening at grid level. A lot of them are grid following. Yeah, so this now calls for new ancillary services. As I've said, utilities are beginning to calculate minimum initial levels, but in reality, these minimum levels always existed, but the market solution guaranteed they were satisfied. So this was because all energy came with initial energy attached, which was free, as I've said. So as renewable penetration increased, the inertia from synchronous units committed for energy production may not provide sufficient levels of inertia. This will be more common when reserve provision for new technologies increases. So if more inertia is required, then it becomes necessary to treat it as a specific service and not just a byproduct of a synchronous generation being dispatched. Power systems facing this scenario are starting to procure inertia. So we are now in that area, or will be soon, procuring inertia from generators. So basically that means it becomes part of the ancillary services suite, and we will have to pay for it now as a reserve, like we have been paying megawatts as reserves. But now we have to say, okay, fine, how much inertia do you have? And then we start procuring this thing. So that's where we are going. And a lot of other guys are already, you know, designing this product and getting it from the market, like the Grid, as I've said, through the DS3 program. They're doing that. The National Grid via the Stability Pathfinder, as I've said, post that event, they went out on tender, a huge tender called the Stability Pathfinder, and that they're actually getting this stuff, services from the market. So that's what's happening. So we don't want to see an event before we before we start doing these things. We better start learning from our international counterparts, especially guys that are weakly connected, and start doing these things. Critical considerations, operation policies. We need to devise this and put these things in critical so that now they can be more enforced. You know, so that every generator that connects knows that this is how things are supposed to be done, just like we are doing with ancillary services currently. So we have to start putting these things in the electrical to enforce them more. And then in terms of the future system studies that we need, obviously it's no longer going to be business as usual. We have to now start learning a new type of studies. We need to start understanding, especially around the new technologies, developing models around that, PV, wind, battery converters. We need to start understanding that and incorporating them in our current models so that we can study this phenomenon a bit better. It's not something that is trivial. It requires a bit of thought because these are new stuff, but it's things that we have to do in terms of reasonable future scenarios as well. We have to think of those scenarios that will be beneficial in studying. We don't necessarily study almost everything, but we have to be selective in terms of what we are studying and develop nice scenarios so that we can make conclusive decisions. And the key takeaways are that inertia is a concern for many utilities. Technologies exist to supplement this. Studies are essential to determine inertia shortfall in future studies and guard against security issues. As I've said, utilities are looking at voltage and frequency together for inverter-based generation that is defining a stability product as opposed to separate frequency of what is voltage studies. So basically, some utilities are now starting to look at this as a more comprehensive type of study instead of just saying, okay, fine, it's a frequency problem. They are obviously trying to look at the other stability concerns because it has to be so. You cannot just isolate it to be a frequency problem, although the root cause might be frequency, but you have to start looking at other stability concerns as well. So bringing it home, as penetration levels of inverter-based generation continue to increase, power system inertia will decline. Thus, South African system operator, with the help from relevant stakeholders, should proactively meet these challenges using mitigating measures mentioned here. Of primary importance is that DOE, I think it's DMRE now, should institute power system studies for long-term planning and short-term operations on the horizon, involving all relevant stakeholders in order to inform future IRP energy mixes post-2030. System operators should develop an increased situational awareness of system inertia, that is ensuring primary frequency response capability from all generation sources, including inverter-based generation, and introducing the use of various forms of FFR as necessary. That brings me to the end of our presentation, ladies and gentlemen. I hope I didn't go over time. I think it was quite a mouthful. I think at this stage we can take questions.
Thank you. Thank you, Mr. Rampokanyo. Very, very insightful presentation. We do agree with you as a center that engineers see things for what they are, and we do need to be vocal and voice those concerns if and when we do come across them. We are very happy that we have a very engaged audience, and there are a number of questions. So looking at the time, let me just get to them. The first question is from Pervalan Govender, whose question is, are inverter tests being standardized in South Africa considering Rokoff?
Well, thanks a lot, Kumuto and Kevin, for that question. Inverter test currently, as I know.
Sorry, I think I was muted. I was talking to myself. So yeah, sorry about that. Yeah, so I'm just saying thanks a lot, Pevelin and Kumuto, obviously, for that question. Inverter test, as I understand, in South Africa, are not been done. I know that there's an initiative from CSIR. There was an initiative to start doing some inverter tests, but that is still a long time coming. But currently, as far as I know, there is no test for inverters for Rock-off, but it doesn't mean that there are no initiatives. I know for one in CSIR, there was a particular one where they wanted to collaborate with ESCOM. In fact, I am part of the studies team that is doing that, but I'm not necessarily part of that particular inverter one. Some more on the Inertia side. There's a collaborative study that CSIR and ESCOM is undertaking, and I'm part of that. I'm leading a few things there. But yeah, it's something that needs to be looked at. A lot of laboratories are coming up, around the world where they are testing inverters for stability, and they're doing it, in a laboratory setup where they are basically simulating, and they're doing it on real-time simulators, So that we need to go there. I know that a couple of institutions in South Africa have bought these real-time simulators, but I haven't seen a test lab that is doing this. But I'm sure in future it should come.
Thank you, Pevelan, for that question. We have a number of questions, so Pevelan, I'll get to your other questions later. Hilton Bartman asks, are these extra costs of supporting technologies to assist with frequency, etc., due to inverter-based generation considered when the costs of renewable energy generation is considered? I don't know if you can answer that, but your opinion on that. Short, just if there's a short answer to that, we would appreciate.
Okay, so are we considering the cost of these new services into the cost of building renewable energy plants? Basically, that's what the question says. Obviously, as and when we start defining the market for these things, then that cost will be catered for. But it's up until the powers that be, especially the system operator, defines these services and what it requires, that now these things could start being incorporated into primary energy costs in terms of building the plant. Yeah, we are not yet there, but I think it will probably come at a later stage. Don't know if I answered the question.
Thank you, Hilton. The next question is from Harun Sheikh. Is the challenge of inertial rigidity only prone to grid-connected inverter-based generation? Are off-grid or hybrid systems susceptible to the same root, to the same Rokoff as a result of the reduction in system inertia?
Thank you for that question. Thank you for that question. I think you have answered yourself in a way. Look, off-grid systems, if they're off-grid and they're autonomous, that means they're separate from the grid. So they do their own thing. So they won't be affected. But we are in an energy transition. Not everybody can afford to be autonomous, Everybody, yeah, the bulk of the population still needs to depend on the grid, and we cannot just be careless and say everybody for himself be autonomous. We are still centrally controlled, and in as far as we are still centrally controlled, largely in South Africa, we have to worry about this thing because it becomes irresponsible not to worry about it. But yes, you're right. If you're off-grid, absolutely no problem. If you're in a microgrid somewhere that is autonomous, even if you're linked with the main grid, that's exactly where I said the future is going. We are transitioning. So up until we see the full transition into renewable energy, where we have microgrids that are autonomous, then it's then that we can start. We can stop talking about this. But because we are in the transition period, we still have to worry about it. But if you're a microgrid with grid forming inverters, you can easily island yourself and supply yourself and you're autonomous. So So that's where we are going. But before then, we are still in the transition, and we have to manage things responsibly. Thank you.
Thank you for that question. I think I'm also mindful of time. We apologize that we have slightly run over, but I guess there are a lot of questions. The next question, I think I'll probably take two more and one from the chair so that I don't get into trouble. The next question is from Kululi Mabula, who says, what is your comment on the installation of synchronous condensers, maybe near inverter-based parks?
Beautiful question, beautiful question. Yeah, probably because of time, I couldn't elaborate more on that. But yeah, look, synchronous condensers, what's happening is that I had said initially that majority of inertia is derived from your turbine tray. And I said that the rotor contributes about one third of that particular total inertia that comes from a generator. So when you're operating a machine in synchronous condenser, you basically decouple the rotor from the turbine. So basically there's no prime mover anymore. And then the system or the machine floats on the network, you know. It sort of like it just follows the network, you know. So it's decoupled from the turbine, and it's no longer generating megawatts, but it's more like generating reactive power. So in synchronous condenser mode, it's one area that we have to look at, even though we know that the rotor itself is not that, it's decoupled from the turbine, which has the larger inertia, but it gives something to the grid. It still gives something to it. So if I think ESCOM is involved or has a project where they are probably looking at retired coal-fired station to repurpose them and to start using them as synchronous condensers, so that now they can start contributing to this inertia. So yes, everybody is looking at that. They are very useful. If we put them in, we have the rotor there. It's massive. It's rotating. They are correcting our voltages. We know how synchronous condensers work. You know, they are very dynamic as far as voltage control is concerned on the network. So if we can repurpose plants like that, number one. Yeah, thank you.
No, yeah, thank you, Mbedi. This topic is very, very interesting. We have run out of time. We hope to have more engagements with you, even as a center and as the SAIEE. We will surely invite you back via the power energy section and/or the symposium that we're thinking about. Thank you for coming through. Minx, I don't know if you're still on.
Yes, I'm here, Khomotso.
Yes, if you can just wrap up for us in the last 30 seconds. I apologize.
Excellent. Mpeli, thank you very much for an informative webinar. As I can see, there is quite a few questions from attendees. I will download all the questions and send it to you for answering, and then we will upload it onto SAIEE website for your information. Thank you very much, Gauteng Centre, for a wonderful putting together this wonderful webinar. Mpeli, thank you for availing your time, for sharing your presentation with us. As I mentioned, the recording of this webinar will be uploaded on the SAIEE TV channel. You can quickly look at the chat box. You see all the SAIEE benefits, how to join us. Look at our CPD upcoming courses, and also you can download the latest issue of the What Now July, the July issue. August issue will be released by the first week of August. Ladies and gentlemen, that concluded our webinar for tonight. I thank you very much for attending, and stay safe and stay warm. Good night.
Thank you.